Hey everybody, welcome to today's lecture, and it's a continuation of the previous lecture, which was on kinematics using the Jacobian. So I have rather inventively called it Kinematics Using the Jacobian Part 2. So in last week's lecture, we had a two-jointed, two-dimensional arm, and we looked at how to get the Jacobian. And if you remember, the Jacobian is a way of relating the velocity of the end effector to the velocity of the joints, right? So we had this two-dimensional, two-jointed arm, so we used some trigonometry to figure out the transformation matrices, and then we took the partial derivatives, and that allowed us to get the Jacobian. Okay, so that's pretty cool. But what happens if we have many joints? Like, so we have an arm that's not just two-jointed, it's n-jointed, and it operates in a 3D space. Okay, so suddenly the problem gets a lot harder. So let's sort of break it down. Let's think about this in steps. So if we think of a single joint operating in 3D, the joint can be either prismatic or revolute, as we've been talking about all this time. So let's take the example of an arm of a joint that's prismatic. Okay, so if the joint is prismatic, then it just extends and retracts like this, right? So if we've got an end effector and we're extending and retracting our arm, that end effector is not rotating, right? So if we wanted to figure out what the rotation is based on the parameter of the joint, it's zero, right? It doesn't matter what velocity my joint is going at. If it's prismatic, it's not causing any rotation. So I can see my omega, which is my angular velocity of the end effector, is equal to 0. Okay, but what is my linear velocity like? Well, so for the linear velocity, the end effector, we know it moves in the z direction, right? So if I've got a single joint and I know that it's moving upwards by 1 meter per second in the z direction, then the end effector must also be moving upwards by 1 meter per second in the z direction, right? Because there's no transformation necessarily. We've just got a single joint in 3D, and the end effector is on the end of that joint. So however fast the joint is moving, the end effector is moving the same amount, right? So we can say that the linear velocity of the end effector is equal to the linear velocity of the joint multiplied by k. Now, what is that k? Well, the linear velocity of the end effector is a scalar. Of the joint, sorry, is a scalar. So we need to multiply it by a unit vector in the z direction so that we can figure out some direction to this motion, right? So by putting k, which is just going to be 0, 0, 1, if you can picture it, it's just a vector that is a unit vector in z. Then if I multiply this, I basically get that my linear velocity is in the z direction and has a magnitude of q dot. Okay, so that was kind of straightforward, and that's pretty cool. What happens with a revolute joint? A revolute joint is a little bit more complex. If the joint is revolute, then we can say, well, however much the angular velocity is of the joint, that's the same as the angular velocity of the end effector, right? So basically, if I've got this joint and I rotate my joint by 10 degrees, then the end effector is going to rotate by the same 10 degrees, right? If you picture this system over here, if I rotate around my z-axis by 10, this triangle, this end effector is going to rotate by the same 10 degrees, right? So it's going to have a angular velocity that's equal to the velocity of the joint, right? Again, multiplied by k so that we can denote what direction that rotation is in, right? Or which axis it's around. But the other interesting thing is that the end effector, when I rotate here, it moves as well, right? Because I've got a rotation, I've got a link, and then if I rotate around here, that end effector is going to sort of move this way. Okay, I hope you can all see that. It's kind of like if I've got an end effector here and I rotate, the end effector didn't just rotate, it also moved, right? So the first question is, in which direction did it move? So if we look at this system over here, I'm rotating this way. So picture I'm rotating around k, which is my z-axis, right? Because remember we said k is a unit vector in the z direction. If I sort of stuck my hand around the vector k and sort of turned it, if I sort of twisted this joint this way, r r is my link that goes to my end effector, and the end effector would sort of go this way, right? So looking at it, the end effector will move in a direction that's perpendicular to the unit vector in the z direction. So it'll be perpendicular to the z axis and perpendicular to r, which is the link between the end effector and that joint. Okay, so that sort of helps because it helps us decide in which direction the thing moves. If we look at the equations that govern this, we said that our angular velocity at the end effector was just equal to our joint velocity, right? Because if we rotate it by 10 degrees, we rotate by 10 degrees on this side, and k was just giving us that axis, right? It's giving us the unit so that we know in which direction we rotated. The linear velocity will be equal to q dot k cross r. Okay, now the cross product, if you remember from your linear algebra courses, gives you a vector that's perpendicular to its two terms. So in this case, our terms are k and r, which is this vector and this vector. So the cross product gives us a vector that's perpendicular to those two. So this vector, right? And that's pretty cool because that's exactly what we want. This is one of the cool things about robotics, I think, is that, when I did linear algebra, and I don't know if it was the same with you, they basically told us, look, here's what a cross product is, and this is how you calculate it. And there was never any sort of idea that, hey, this is useful because it helps us accomplish something. It was just, you had exams that said, or calculate the cross product between these two vectors, and so you did, but you never really had a good idea of why, right? So with robotics, you can start to see these things matter, right? I needed, in this case, to get the vector that's perpendicular to these two, and that's what the cross product does. The cross product has a magnitude, which is sort of the area of the two vectors. And in this case, because this is a unit vector, it's just giving us a magnitude of r, so it's fine. And we multiply that by our scalar q dot, because however much we rotate by, we want to say that this thing is moving faster in that direction, right? Obviously, the faster I spin around k, the faster the end effector moves. So I've now got these relationships for a revolute joint. The angular velocity of the end effector is equal to the velocity of the joint multiplied by k, and the linear velocity of the end effector is equal to the joint velocity multiplied by k cross producted with r, which is the vector joining the end effector to the joint. Okay. I hope that made sense to everybody. But that's so that's pretty cool, but it's for a single joint that the end effector is just directly connected to. What happens if you have multiple joints? Well, then what you have to do is figure out the contribution of each joint to the velocity of the end effector. So if there's one joint that's making the end effector rotate by 10 degrees and another one that's causing it to rotate by 20 degrees in the same axis, that means it's going to just rotate by 30 degrees, which is great, right? Maybe there's one that's causing it to rotate by 10 degrees in X and another one that's causing it to rotate by 10 degrees in Z. Then you've got those two 10-degree rotations. So it's quite easy to combine these different effects, right? But the trouble is that each of these joints is operating in their own axis. So if I say I'm rotating by 10 degrees around Z, that's not the z-axis of the end effector. That's the z-axis of that joint. Okay? But then how do I transform from the axis of that joint to the axis of the end effector? Well, I use the transformation matrix. Okay, so we just need to transform the unit vector k to be in the world frame. Because if you look at this system, we were saying that it's doing a motion of q dot, but in the z-axis, right? But now the z-axis is the z-axis of that joint. the vector will be completely different when I transform it to the world frame, which is the frame I really care about. Okay. So if we do that transformation, we basically have to take the transformation matrix ti minus 1 naught and apply it to k. So the first question is, why ti minus 1? Well, that's just because the axes are numbered from 0, but the joints are numbered from 1, right? So joint 1 is on axis naught, and joint 2 is on axis 1, and joint 3 is on axis 2, and such. So if we're talking about joint 1, it's on axis naught. If we're talking about joint 2, it's on axis 1. So for joint 2, we'd be using the transformation matrix T1 naught, right? Because joint 2 is on axis 1. So we need to apply that relevant transformation matrix to that unit vector k. So if we look at a sort of general form of our transformation matrix, we have like the sort of x component, the y component, the z component, and the origin component, right? This is the part of the transformation matrix that handles the translation, the movement along x, y, and z, and these handle the rotations around each of these axes. We want to multiply it by a unit vector in the z direction, so this naught, naught, 1, naught. Okay, and what we'll get is zx, zy, zz, naught. Okay, so basically that means when we talk about k in these equations, in our head initially it was naught, naught, 1, but because we're transforming it, we now, instead of using naught, naught, 1, we use the z component of the relevant transformation matrix. Okay, that sounds more complex than it is. I think it'll get easier with a bit of an example. So let's look at what we do for the angular velocity Jacobian. Okay, so with the angular velocity Jacobian, the whole point of having it, if you remember from the last lecture, it was so that we could relate the angular velocity of the end effector to the velocities of each of the joints, right? And if you look at it, you've sort of got a pairwise multiplication here, right? It's a dot product. So if I take the Jacobian like j underscore 1, the Jacobian relating to joint 1, it'll get multiplied by the joint velocity of joint 1, and similarly for all the others. Okay? And that'll get me some angular velocity in the end, right? Now, in this system, what this Jacobian is then doing, what this component is doing, is it's saying what's the effect of joint I on the end effector. So remember, if the joint is revolute, it's just q dot k, and k is the z component of the transformation matrix, right? So that means the Jacobian component sort of, it's sort of per joint. The Jacobian relating to joint I is just zx, zy, zz, or the z component of the transformation matrix T I minus 1 naught. Okay. Again, this is where I would probably get questions. And so if there's something you don't understand, feel free to ask about it in the Discord group. We unfortunately don't have the live questioning in the lecture like we do when we're all sitting in the class. But basically, I'm just putting the k's in here fundamentally, where each k is the z component, and I can do that because the effect is q dot k, so it's going to become k times q dot k times q dot k times q dot, right? And as an example, let's say we have an RRP arm. So that's one where the first joint is revolute, the second joint is revolute, and the third one is prismatic. Okay. If we've got transformation matrices as presented below, we can figure out what the angular velocity Jacobian looks like. Okay, so let's look at these transformation matrices. So I just got a shorthand here. C1 is cos of Q1, S1 is sine of Q1, C2 is actually cos of Q2, just because this would become a nightmare to write down if I expanded it all over the place. So this would be like minus cos of Q1 sine of Q2. Okay. So we've got these transformation matrices, and then the question is, what does the angular velocity Jacobian look like? So with the Jacobian, we're basically going to end up with a matrix where each column is the contribution of each joint. Okay, there's 3 joints. So the first column is going to be the contribution of joint 1, right? The contribution of joint 1 to the rotation of the end effector, well, it is a revolute joint, so that means, it does contribute to the revolution of to the angular velocity of the end effector. And the question is, how much does it contribute, right? To what magnitude? Well, what we said was that I have to take the z component of the transformation matrix Ti minus 1 naught. Now I'm talking about joint 1. So that's going to be the transformation matrix T naught naught. Okay. Now looking at these transformation matrices, this is T1 naught. This is not T naught naught. So I don't really want the z component of this. I want the z component of T naught naught. What is T naught naught? How do I transform from axis naught to axis naught? What would I multiply by? Okay, hopefully you said the identity matrix, because the identity matrix doesn't do anything. So if I want to transform from the reference frame I'm in to the reference frame I'm in, I don't want to do anything, right? So the transformation matrix will be the identity matrix, and the z component of the identity matrix looks like this. It looks like 0, 0, 1. Okay, now this is important. This trick is one that a lot of people are going to get caught by. It's sort of tempting. It's sort of intuitive. Well, it's the first joint, so I take this z component. No, I don't, right? This z component is for T1 naught, and T1 naught transforms from the axis of joint 2, right? Joint 2 is in reference frame 1. Okay, so I need to use 0, 0, 1. And that does actually make intuitive sense, right? Because I'm rotating by 10 degrees in the base frame, right? In reference frame naught. So that means the end effector is going to rotate by 10 degrees in reference frame naught. I don't have to do a transformation because I'm in the base reference frame. Okay, so for my RRP arm, this first component is 0, 0, 1 because I don't have to do a transformation. I'm already in reference frame naught. Okay, for the second joint is in reference frame 1. So that means when I take a z component, I need to take the z component of T1 naught. So I'm going to take this minus S1 C1 naught, this one here. And I'm going to stick it here, right? Again, it's joint 2, which means it's in reference frame 1, which means I take this z-axis, not this one. Okay? Then for my third joint, what contribution does it have to the end effector? Now, again, it's tempting to say, well, I'll take this component and stick it here. Okay, because that's what I've been doing. I've said, well, it's the third joint, so it's in reference frame 2, so I take this z component. But the other important point is that the third joint is prismatic. And that means that nothing I do affects the angular velocity of the end effector, because it's the sort of joint that extends and retracts. So its joint velocity is making that joint extend and retract. It's not making the end effector rotate, right? It's not causing any angular velocity. So that means the Jacobian component that applies to the third joint is going to be 0, 0, 0. Okay. I hope all of that made sense. But so basically, I've got an angular velocity Jacobian that looks like this in the end from these transformation matrices. Okay, so the next thing is, what do I do with this Jacobian? So I've got this Jacobian. Now let's say I said, okay, well, I know that joint 1 is rotated at 0 degrees and is rotating at 2 radians per second. Joint 2 is at minus pi over 2 and rotating at 1 radian per second. And joint 3 is fixed at 5 meters. So it's not moving, but even if it was, it's extending or retracting, right? Then I've got the same equation I had in the previous lecture, that the angular velocity of the end effector is equal to the angular velocity Jacobian times the joint velocities. And I know what all of these terms are. The angular velocity Jacobian is this thing, but I can substitute in my angles. So this becomes minus sine of 0, and this becomes cos of minus pi over 2. And I end up with this Jacobian after substituting in those values. Q dot, which is the vector representing my joint velocities, well, the first joint has a joint velocity of 2, the second joint has a joint velocity of 1, and the last one has a joint velocity of 0. So if I take this and multiply this, I end up with this angular velocity. So basically, if I had this arm and I was rotating here at 2 radians per second and this one at 1 radian per second, my end effector would be rotating by 0 degrees, by 0 radians around the x-axis, by 1 radian per second around the y-axis, and by 2 radians per second around the z-axis. Okay, so I could transform my joint velocities to an end effector velocity because I have this angular velocity Jacobian. Okay, I hope that that wasn't um, incredibly awful. I'm not really sure. Okay, so that covers the angular velocity Jacobian. Maybe pause, grab a drink, relax your mind a little bit. Then we're going to get to the linear velocity Jacobian. Okay, so the linear velocity Jacobian is an interesting one. If the joint is prismatic, we said that the linear velocity is just q dot k, right? So the Jacobian will just be k, because remember, the velocity, the linear velocity is equal to q dot times the Jacobian. So the Jacobian is just k. And of course, same as we did with the angular velocity, we have to transform that to the world reference frame. So it'll be the z component of the transformation matrix T I minus 1 naught. Sorry, that should be an I, not an N. I'll fix that in the slides. So basically, we just do the same thing we did for the angular velocity of the revolute joint. That's the same as the thing for the linear velocity of the prismatic joint, right? We just directly take that k and call it the Jacobian. But if the joint is revolute, remember we had this relationship that v equals q dot k cross r. Now this r is an interesting one. When we were looking at a single joint, we said that it's the link from the base of the joint to the end effector. Okay, and we carry on that principle in an end-jointed arm, and we say that r is the distance between the joint axis and the end effector. So think of it as sort of a virtual link. It's not a real link, because like let's say we have a 3-jointed arm. Joint 1 is not directly connected to the end effector, but you can picture a sort of virtual vector connecting the end effector to the first joint, right? So if I had, say, my elbow and my end effector, they're connected by this thing here. But if I have my shoulder and the end effector, they're not. But you can sort of picture a sort of virtual line connecting the two, right? So that'll be my R in this case. And so R is just going to be the origin of the end effector reference frame minus the origin of my joint reference frame, right? So it's O n naught minus O I minus 1 naught. And the O components are from the transformation matrix here, right? So remember, this component handled the sort of translation. So it handled where the axes were in space. Okay, so R is just my end effector reference frame origin minus my joint reference frame origin, to sort of give me that sort of virtual vector connecting that reference frame to the end effector, right? And then V was equal to Q dot K cross R. So it's Q dot times the Z component, right? Because that's what K was. We worked that out previously. So it's the Z component of the I minus 1th reference frame crossed with that R. Okay. So our Jacobian is just the Z component crossed with that R, right? The subtraction from the origin vector. And if it's again, if the joint is that's if the joint is revolute, and if it's prismatic, it's just the Z component of the transformation matrix. We don't have to do the cross product there because it's prismatic. There's no need to find the perpendicular vector and all of that. Okay, so let's say we had the same RRP arm as before. Now, this is an interesting one. So now, what does our Jacobian look like? So again, the first column is going to be the contribution of the first joint to the linear velocity of the end effector, right? So that means it's going to be the Z component of my 0th transformation matrix of T naught naught, right? There's going to be this thing here, which is just naught naught 1, right? Remember, we talking about reference frame naught, so it's the identity matrix, and the Z component is naught naught 1, cross producted with the difference between the final origin being this thing minus the joint's origin, which is naught, 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 right? It's naught, naught, naught because I'm in the base again, right? So the origin of the base is naught, naught, naught in the base. So basically I get something like this. I've got naught, naught, 1, which was my z I minus 1 naught. Take the cross product with this minus naught, naught, naught. So that's just this, right? So I've got this thing minus Q3 C1 S2 minus Q3 S1 S2 and 3 minus Q3 C2 just directly from the origin thing. And when I take the cross product, I get this thing, right? So if you've forgotten how to calculate a cross product, please go and look it up. But basically, if I want the first sort of component, I block off this thing and I take that it's this diagonal minus this diagonal. But this diagonal is 0 because 0 times anything is 0, and this one just becomes Q3 C1, Q3 S1 S2 because it's this minus this, right? So I get this thing. And then the second component is this minus, this minus this. But this is just minus Q3 S1 S2, and this is 0 because I get, so then it just becomes minus Q3 S1 S2. And the third component, I block out this, and it's just this minus this, but there's zeros on both of these, so you get 0 here. So the first component here, so the contribution of the first joint is going to become Q3 C1 S2 minus Q3 S1 S2, 0. Okay, now for joint 2, it's also revolute, so I have to take Z1 naught and cross product it with the difference between those two origins, right? So Z1 naught is this thing here, minus S1 C1 naught, and I take the cross product with this minus this. Okay, now the only thing here is this minus 3. So other than that, this is minus 0 and this is minus 0. So we end up with this expression, right? Minus Q3 C1 S2 minus 0, minus Q3 S1 S2 minus 0, and 3 minus Q3 C1, 3 minus Q3 C2 minus 3. So you just get this thing, okay? And another interesting thing here is that you've got this Q3 S1 squared S2 plus Q3 C1 squared S2. And because sine squared plus cos squared is equal to 1, right? This is sine squared of Q1, this is cos squared of Q1. We can take that out as the common factor, and we end up simplifying to just Q3 S2. So we end up with this as the second component. Okay, then for the third component, now the third component is an interesting one because the joint is prismatic. And because it's prismatic, we don't have to do any of that cross producting. We just take the Z component and we just paste it in there. Okay, it doesn't need we don't need to figure out what's perpendicular to it or anything like that. We just, basically we're taking the unit vector and transforming it with the second axis's transformation matrix, or the third axis, if you're counting that way. And you end up with this Jacobian. Okay, so now this is the full linear velocity Jacobian. So there's an example here. Find the linear velocity of the endpoint when joint 1 is at 0 degrees and is rotating at 2 radians per second. Joint 2 is at minus pi over 2 degrees and rotating at minus 1 radians per second. And joint 3 is extended to 2 meters and not moving. Okay, so I want you guys to take care of that. I'm not gonna do it, but basically you just need to substitute all the things in and then multiply it by the appropriate Q dot. Okay, so remember the Q items are the parameters in here and the Q dot items are the ones that we multiply by. And that's how we'll get the linear velocity. Okay, so that was, yeah, that was something, wasn't it? I think if this is sort of confusing at the moment, again, feel free to ask questions in the Discord group, but you will also get TUT questions, and sometimes working through the TUT questions helps you realize why this is not quite as hard as it looks. The really powerful thing, I spent a lot of time in the lecture giving you the rationale behind what you're doing, so you're transforming in the z-axis and stuff. When you're doing it, the advantage is you don't have to care. You just algorithmically apply the thing. Well, I take the z, I cross product it with difference in origins, or I just take the z and I paste it in there, or I just take 0 and I paste it in there. Depending on whether you're doing the linear velocity and angular velocity, or angular velocity, and whether your joint is prismatic or revolute. But so you just kind of apply it algorithmically, which is great, right? Like, it's always nice when we get stuff that we don't really have to think about, because every time we have to think about something, we have the potential to think about it wrong. In this case, we're just gonna follow the algorithm and get the Jacobian. Okay. So the last thing I want to talk about in this lecture is statics, right? So if we look at what we've been doing up to now, we've been relating the joint state and joint velocity to the end effector state and the end effector velocity. But often we're not operating in terms of velocity or in terms of position, right? So we said the reason we wanted to think about velocities is because we don't generally have control over the state, we have control over the velocity. But often it's worse than that. We don't have control over the velocity, we have control over the forces. So that means we have to start to think about how we apply forces to joints to get particular outcomes. Okay? So picture that there's an arm, and at the end effector of the arm, we've got a weight, right? So we've stuck a weight on there. And sorry, not completely over the flu. So if the system is at rest, so it's not moving, then that means that the forces acting on the end effector are balanced out by the joint forces, right? So basically we've got this weight, but the arm is not moving. So that means there's some joint that's applying a torque, or otherwise the whole system would like sort of fall down, right? So if the system is at rest, we know that that's not the case, and so we know that the forces are balanced. Okay, so if it's at rest, we're saying that the work that the end effector or that the weight is sort of applying on the end effector is balanced out by the work done by the joints. Okay, and the work is the force multiplied by the displacement. So if we take the force applied at the end effector and multiply it by the displacement of the joints, that should be equal to the joint torques, right? So the force applied at the joints multiplied by the displacement of the joints, right? Now, nothing's moving, the thing is static. So talking about the displacement of the end effector and the displacement of the joints is kind of silly, but it's not really, because basically what we're thinking about is a sort of concept of the displacement. It's not the actual displacement. Basically what we're saying is that, like, if this is causing some sort of virtual displacement and this is causing the same virtual displacement, that's the reason the thing is not moving, right? But if the joints weren't applying that torque, there would be a displacement at the end effector. And similarly, if the end effector didn't have this weight on it, there would be a displacement on the joints, right? But because these two things are in balance, we the system is not moving. So here, in order to get these multiplications to work, we have to transpose. We have to say that the force transpose times the sort of virtual displacement of the end effector is equal to the joint forces or joint torques transposed multiplied by the displacement of the joints. All right. But one cool thing that we know is that the displacement at the end effector is the Jacobian times the displacement at the joints, right? That's the whole point of the Jacobian. It relates displacement in the end effector to displacement in the joints to displacement in the end effector. So if we take this relation and we multiply it back in, we get that the force transpose times the Jacobian times the delta theta, which is the change in the joint states, or the displacement in the joints, basically, is equal to our joint forces or our torques transposed multiplied by our joint angles. So that's cool, because then we can take this delta theta out of the equation, and we just get that F transpose J is equal to tau transposed. And that means we get tau equals the Jacobian transpose times the force. Okay. Again, that's a derivation you don't particularly need to know when you're when you're doing this, but you do need to know that tau, which is the joint forces, is equal to the Jacobian transpose times the end effector forces. Okay, so what's this for? Why does it matter? Well, the thing is, we already know how to get the Jacobian, right? So that's cool because we get to leverage the knowledge we had before. And what we can do with it is we can say that if I have a weight on the end effector and I don't want the system to move, what force should I apply at the joints? Okay, so let's take that RRP arm we had earlier. We've got this Jacobian. And if joint 1 is at 0 radians and joint 2 is at minus pi over 2 radians and joint 3 is at 2 meters, I can substitute that all in here and get the Jacobian. So it's our linear velocity Jacobian is this thing here if I substituted all the items in there, right? And I know that tau is equal to the Jacobian transpose times the force. So let's say the arm is carrying a 10 kilogram weight. That means there's going to be 100 newtons of downward force in the z direction, right? Because I'm sort of pulling downwards on the arm, right? So the end effector has got a force of minus 100 operating in the z direction. Now, if I take the Jacobian and I multiply that by the force, what I'll get is I'll get tau, right? Tau is Jacobian transpose times the force. So I take the Jacobian, I multiply it by my force, and I get this vector 0, 200, 0. And these are now my joint forces. So if I don't want the system to move, I can apply a force of 200 Newton meters to keep the system static. Okay, so I've managed to calculate what force I need to apply at joint 2 to keep the system static. Okay, and obviously this is only useful if what you want to do is keep the system static, but that's what this part of the lecture was about. In the next lecture, we'll look at systems in motion. So that's a discussion of dynamics. Okay, and that one's quite an interesting one as well. But I think we've covered quite enough for this lecture. Again, I think if it does feel confusing, doing a TUT will help because it sort of gives you an idea of what parts of it you need to apply and what parts of it it's nice to be aware of the derivations, but you don't really need to know them. So yeah, I hope you enjoyed the lecture, and I'll sign out with another with a picture from my son. He said that I need to show you guys his robot design so that hopefully you guys can build it. I don't know if you guys can see that. Yeah, that's his robot. Hopefully one of you is going to build it and work out the Jacobians and such. Okay, thank you all for listening. Bye.